So by the end of this chapter, we should be able to recognize what a continuous probability density function is, just in general. And then those apply to continuous probability distributions, and we will look at two specific continuous probability distributions, the uniform and the exponential. So in section 5.1, we talk about continuous probability distributions. Recall that we have a random variable. A random variable is a numerical variable that describes, this also sometimes we'll say takes on, the outcomes of an experiment. So the outcome of an experiment will be a number, and a random variable will take on that value. We usually notate random variables using capital letters, usually X, but it wouldn't have to be, it could be Y. There are two types of random variables. The first is discrete. Remember, these take on values that can be counted, as opposed to the continuous random variable, and this can assume all values in a given interval. So things like measurement, time, money, etc., these are all continuous random, can be represented by continuous random variables. Also remember that in the discrete probability distribution, again, a countable number of values, and because of that, we used a table of all values for that random variable, and then we listed the corresponding probabilities, and when we did that, we created a discrete probability distribution. Now we'll be looking at continuous random variables, and the values of X cannot be counted, so they cannot be placed in a table since the outcomes are measured. So we're going to have to use a graph or a formula to represent this distribution. But first, let's understand some properties of the continuous probability distribution. Okay? So this graph that we will use of the continuous distribution is a curve. It gets called the density curve, and the probability is represented by area under that curve. We call the curve the probability density function. We abbreviate this the PDF. And we use the symbol lowercase f of x to represent this curve because it is a function that represents the graph of the distribution. Now, probability is the area under the curve, and to calculate that, we're going to need a different function. That is the cumulative distribution function. We abbreviate this the CDF. It will calculate the area under the curve, and hence the probability. To notate this function, we use a capital F of x, and this is the function we will use to calculate the probabilities. Okay, so let's look at a few continuous probability distributions. The first is the uniform distribution. The uniform distribution always has the shape of a rectangle. Here, we would use the curve is represented by this line. It is a horizontal line. It is y is equal to some constant. So our probability distribution function, f of x, the PDF, will just be equal to whatever that constant is. This is in the uniform distribution. Exponential distributions have this shape, like so. And in this situation, this curve here represents the probability distribution function. This is our little f of x, or the PDF. Then, in the next chapter, we're going to look at something called the normal distribution. The normal distribution has this shape. In this case, the curve is here. This is our function little f of x. It is the probability density function. It is the graph of the distribution. So the area under the curve for the uniform is inside of here. And if we wish to calculate any probabilities, like say for example here, we will have to use capital F of x. For the exponential, the area under the curve happens here. And again, we could calculate just a portion of it. to do that, we would need to calculate the probabilities, we would calculate the area, and we would use a capital F of x. This capital F of x will be different from the uniform. And lastly, in the normal distribution, the area under the curve happens here. It also has its own capital F of x that will calculate the area. But the important connection here for the moment is that about the relationship between probability and area under the curve. The entire area under this curve and above the y-axis is equal to 1 because this is a probability density, a probability distribution. The sum of all probabilities must be equal to 1, and hence the area under the curve must also equal 1. With continuous distributions, we are going to find probability for intervals of x values rather than for a single value of x. So say, for example, we would be looking at the probability where x is less than some constant, not the probability where x is equal to a constant, where we had done, like we had done in the discrete distributions. So if we're saying that the probability that x goes in between c and d is the area under the curve above the x-axis, it is to the right of c and to the left of d. If we are calculating this probability, it will be c less than x less than d. That is the same as c less than or equal to x and less than or equal to d. The reason for that is here. The probability that x takes on any single value is equal to 0. And we can ask why that would be. It's because the area below the curve in between x equals c and, this should say x equals d, has no width. Therefore, there is no area to calculate. So the probability that x is equal to some constant has no area, therefore no probability. The probability of that must be 0.